And the last speaker of the first session is Lingfu Zhang from Princeton. So take it away, Lingfu.
Okay. Can you hear me? Okay, great. Thank you for coming to my talk today, and thanks to the organizers for organizing this wonderful event. So today I am going to talk about a very classical model, which is Anderson localization from mathematical physics. And then I will report some recent progress that I made together with my collaborator, Linjun Li, who is a student at UPenn. So we show that on the 3D lattice with i.i.d. Bernoulli potential, Anderson localization happens near the edge of the spectrum. Okay, so let's start. So the operator we study is a classical random Schrodinger operator with a Bernoulli potential. So we just work on the d-dimensional lattice. And then you take the Laplacian, which is a classical discrete Laplacian on graphs. And then you plus an i.i.d. Bernoulli potential so that your V is like with at each vertex with 1/2 probability it equals 0, and with 1/2 probability equals 1. And that's independent for every vertices. And you also multiply by delta, which is a constant, and also referred to as disordered strings. Okay, so why people study this? So it's the whole story started from the seminal work of Anderson from the 1958, where he used the dynamic driven by this model to study an electron hopping inside a metal and study the conductivity of materials. Here, you can just imagine that at each lattice vertex, there is just an atom, and it can be one of the several different types, and the distribution is i.i.d. For every lattice. Here that models the uniform impurity in this material. Okay, so to study the dynamic of this model, it's crucial to understand the spectrum and also the eigenfunctions of this random Schrodinger operator. So recall that for discrete Laplacian, the spectrum is a continuous spectrum, and in the interval 0 to 4D, where D is a dimension. And it's a classical result that almost surely when you add this i.i.d. random potential, the spectrum shifts by delta and take the union of that. Okay, so the observation made by Anderson in that seminal work is that whereas the Laplacian has continuous spectrum and it does not have any eigenfunctions in the L2 space, with this very little perturbation, so that whatever small delta is, as long as it's positive, then your random operator now almost surely has eigenvalues in L2, and the eigenfunctions are exponentially localized. Okay, and this back then was only like by physicists and by experiments and simulations. While in the mathematic aspect, such Anderson localization is typically defined as follows, and this is notion we use, so that for some interval, if any polynomial bounded eigenfunction, meaning that it's a generalized eigenfunction, it does not necessarily live in this L2 space. Suppose you have such an eigenfunction and the eigenvalue is in this interval, then this eigenfunction must exponential decay. So this is called that the Anderson localization happens in this interval. So a couple of remarks. The first is that this Anderson localization notion is sometimes also referred to as a spectrum localization, to be distinguished from the so-called dynamical localization, which studies which is about the dynamics driven by this random operator, and that's a more complicated object. And the second remark is that this Anderson localization in the interval I implies that this operator has pure point spectrum, meaning that if you just take any number in this interval I where the Anderson localization happens, it's actually an eigenvalue, and there is a corresponding eigenfunction in L2, and that eigenfunction has exponential decay. Okay, so what's our result? We prove that for the Bernoulli potential case, and in the 3D lattice, the Anderson localization happens near the edge of the spectrum. Okay, so here I'm just stating it in terms of the lower edge, but via symmetry, you can see that it also holds for the upper edge. Okay, so let me just give you some of the history of this problem, and mostly related to our work. And there are some difficulties and then breakthroughs, like in like 10 years, 20 years. So it's a long history object. So it came to the mathematics community in the 1980s. Although like before that, physicists have started using simulations or experiments. So there was a breakthrough result by Froelich and Spencer, and then they have like a sequence of works. So that what they did is that they, rather than the Bernoulli case, they work on the case where the random potential has continuous distribution. So that the random potential V at the i.i.d. distribution, you assume that the probability density function, first they did it assuming that the probability density function is bounded, and then later relieved to like with some Holder continuous conditions. Okay, what they could do is that they prove that first, when your disordered string theta is large enough, the Anderson localization holds in the whole spectrum. And second, given any disordered strings and any like potential with bounded density near the edge of the spectrum, the Anderson localization holds. So this is so let me just mention a bit about the general picture of this. Is that this is something like proposed by physicists, and they also have like some heuristic arguments, which says that for dimension 1 and 2, Anderson localization is conjectured to hold in the whole spectrum. So for whatever non-trivial i.i.d. potential you have, whereas for dimension greater or equal than 3, people believe that there is a phase transition if your disordered strings is not large enough. Then meaning that in the bulk, people would expect that there is delocalization and you have continuous spectrum rather than pure point spectrum. Okay, so this conjecture is very far from being verified, except for a handful of cases. In particular, for one dimension, this is verified for like the whole spectrum for any non-trivial i.i.d. random potential. And this was also done in the 1980s. So the case that we're interested in, the Bernoulli case, which is very contrary to the continuous distribution case. So you can think of it like it's the most non-continuous thing that you can think about. Also, there is some like physical reasons why this is interesting. For example, if you study alloy type materials, like at each integer location, you can just have like one or two types of materials. So actually, the Bernoulli case is more interesting from a physics point of view. However, like there were some technical difficulties that prevent people from 1980s to apply the results from with the continuous assumptions. And then a breakthrough was made by Bourgain-Kenig in 2005, where they proved Anderson localization with Bernoulli potentials for all dimensions. But what's happening there is that they are not studying the original model on the lattice. They studied an analog model on the continuous space, so that at each integer location, like around it, you have like a bound function, and with probability 1/2 you have it, and with probability 1/2 you don't have it, and that's i.i.d. error. So that's just an analog of this in the continuous space. And then, okay, they face some difficulties to do that directly in the discrete lattice ZD. And it was more recent, like 13 years since then, like on the 2D lattice, Ding and Smart proved that the Anderson localization holds near the edge for the Bernoulli potential case. And our result does this, verifies this Anderson localization near the edge for the 3D case. Okay, so let me briefly talk about some ingredients, like in all the series of works, and what are the difficulties prevented each of them to go further. So starting from the 1980s and the work of Spencer and his co-authors, they already did some know that it could, like they relies on some estimates on the exponential decay of the relevant, and they use multi-scale analysis, etc. So this is a huge machinery developed by them. And one of the key steps is the so-called Wagner estimate. basically you take like a self-adjoint operator, and so it's like a very general result. So you take any finite dimensional self-adjoint operator, and you take like a i.i.d. random potential added to the diagonal. Then you can bound the probability that there exists an eigenvalue in any interval by just the length of the interval times dimension n, and also times the bound of the probability density. Okay, so you can see that what prevents people from the 1980s to do the Bernoulli case is that there's no such Wagner estimate for the Bernoulli case. You see that in the Bernoulli, like when you do not have the continuity, like the density lambda just goes to infinity. And I need to say that to prove such Wagner estimates for the Bernoulli potential is itself a very interesting and widely open problem. Okay, so the Bourgain-Kenig, they managed to make that breakthrough by sort of getting around of this by proving a Wagner type estimate within this multi-scale analysis, which I do not have time to expand on. But I need to say something about like the starting from the work of Bourgain-Kenig. They could only do analog in the continuous space because they use a so-called unique continuation principle in RD. And which basically says that a simplified version would be that, okay, the classical unique continuation principle, so that you have a harmonic function in the RD, and then if your harmonic function is 0 on some open set, then it must be 0 everywhere. Okay, that's for the continuous space. But such analog is not true for the discrete lattice, because, like, for example, in you can think of yourself like in a 3D lattice, Z3, you can cook up a harmonic function, which is supported only in a 2-dimensional lattice, and it's 0 everywhere else. So, like, it means that even like 0 in most of the places does not mean that this harmonic function is identically 0. Okay, so our contribution, that's our main contribution, is that we prove like sort of like the discrete unique continuation principle, which is okay, it's like weaker than what's happening in the RD, but that's enough to fit into the framework of Bourgain and using some arguments from Dean Smart to prove the 3D Bernoulli Anderson localization. So the thing is just is that okay, there is a way to interpret it in like in the unique continuation principle language, but what we can see is that okay, so suppose you have like a function Laplacian u equals vu, where v is a bounded function, and then you can show that in except for like a lower dimensional where the dimension is 3/2, it cannot be very small. Okay, so I need to say that in Dean Smart, they did some analog thing for the 2D case, but like a direct analog in the 2D does not hold. So they did a probabilistic version so that the V is a random potential rather than a deterministic one. And then they proved that with high probability, such an equality holds. And so you may ask why, like Bourgain-Kenig, like in this previous work, they usually do for all dimensions, while in Dean Smart and our work, we did like 2 dimensions, 3 dimensions, 1 dimension at a time. Basically because like this discrete unique continuation principle is really difficult to establish, and that requires different arguments in different dimensions. And for us, like we use lots of geometric arguments and some polynomial structure of harmonic functions. And I need to mention this harmonic result work by Buhovsky, Logunov, Malinnikova, and Sodin, where they proved Liouville type estimate, and which inspired the arguments in both our work and Dean Smart. Okay, so I guess I'm running out of time, and thank you. I stop here.
Okay, so let's all unmute ourselves and thank all the speakers from the first session.